Good afternoon, I'm Milakovic, and it's an honor and privilege to present at the inaugural Ergodicity Economics conference, of which I hope there will be many more in the years to come. This is joint work that I've been undertaking with Simona Alfarano for a very long time now, and the title of our presentation today is phrased as a question: is there a risk-return trade-off under ergodicity? And to relieve you from the suspense, the answer we give is no. So by way of introduction, let me emphasize first of all that we come in peace and as friends, in the sense that Simona and I have been studying distributional regularities in economics and finance for a long time. And what we generally observe is that these variables are non-ergodic, in the sense that the cross-sectional or ensemble distribution does not coincide with the distribution that you observe if you study the time series of individual agents that make up the system. We do find one exception, and so far we've found only one, and it is not just any old economic variable, but it is the rate of profit, or in more modern parlance, the return on assets, which vitally regulates the metabolism of capital. I have to make a very important qualification from the start, namely that the ergodicity in corporate profitability that we claim here only pertains to those corporations that survive for a prolonged period of time. Now, if we were studying firms that do not survive, then we cannot hope for finding ergodic properties, because if you disappear from the ensemble, how can you be representative of it in the first place? Notice also that survival by itself is not a sufficient condition for ergodicity, because agents or firms in our case might be following different processes, or even if they obey the same process, they could follow different parametrizations of this process, which would make the overall system then again non-ergodic. Does it make sense then to speak of surviving capital in the first place? And perhaps somewhat surprisingly, the answer is definitely yes, because the vast majority of corporate deaths are due to a change of ownership and not to the destruction or depreciation of capital. This means that we observe an accumulation of surviving capital over time, and this, coupled with the perpetual reallocation of capital in search of abnormal profits, which is really at the heart of competitive market economies, leads to an outcome that is quite distinct, both conceptually and empirically, from independent destinies in a growth process, say geometric Brownian motion. By way of illustration, you see here the distribution of growth rates and of profit rates. Profit rates are shown in blue and growth rates in red. And I guess the most important point that I'm trying to make on this slide is that you need to massage the growth rates already quite a bit in order to obtain this unimodal shape here that we observe, which is approximated by an asymmetric exponential power distribution. Because if you do not normalize by the average growth rate in a given year, what you observe is multimodality in the distribution due to the business cycle. Profit rates, on the other hand, shown here in blue, are well approximated by a symmetric double exponential or Laplace distribution. And the data that you see here are raw data, which means we're simply plotting the distribution of the ratio of operating income to total assets for surviving firms in a given year and then pooling them together. The reason why we can pool them together without manipulating the raw data is that the annual distributions are remarkably stable, meaning that the location parameter, which is around 9%, so the average profitability of US non-bank corporations is around 9% per year, rather high, spectacularly high, one might say, and the dispersion is rather low at about 6% per year. The idea that Simona and I then had was to say, well, given that this is the only quantity we find that shows such remarkable stability in its ensemble distribution over time, let us study the time series. So at first we started inspecting the time series, and here are a couple of examples on the left-hand side in this figure. They're not hand-picked in any way. These are just alphabetically ordered. The first company from the first industry, the first company from the second, and the first company from the third industry. And what you observe is, first of all, substantial and significant autocorrelation, which, by the way, is absent in growth rates. And it also appears reasonable to assume that these series are mean reverting, which is perfectly in line with economic theory. Well, there is nothing in economic theory, by the way, that would warrant a mean reversion in corporate growth rates. So in order to model the time series, Simone and I decided to employ a parsimonious diffusion or stochastic differential equation. And those of you who are familiar with these types of animals understand that if you want to obtain a particular stationary density from a diffusion process, you have 1 degree of freedom. You can either fix the drift function and then look at how the diffusion function needs to look like in order to obtain the stationary density that you desire, or you do it the other way around, which is what we did here, heeding the dictum of parsimony and actually also taking into account some economic considerations. We just opted for fixing the diffusion function with a constant that you see here given by square root of d that scales the linear increments. If you prescribe this and you want to obtain a stationary Laplace density, then the resulting drift function is the one that you see here. And since it's the only equation in my talk, I can perhaps spend a little more time discussing it. So first of all, notice that the mean reversion in profit rates, denoted here by xt, is immediately obvious through the minus sign in combination with the sine function. That means if you're below the average profitability in the system, which we denote by m, you will be pulled back up towards m, and symmetrically, if you're above m, you will then be pulled back towards the average profitability. Notice that this is what a physicist would probably call an independent force, because the sine function does not care about how far away you are from the average profitability. Now, also notice that this diffusion parameter d is also showing up in a very peculiar way in the drift function, scaled by 2 sigma, where sigma would be the dispersion that we observe in the Laplace distribution. Now, this stochastic differential equation admits for a closed form transient density, or Fokker-Planck or Kolmogorov-Forward equation, which allows us to estimate the parameters m, sigma, and d from individual time series efficiently with maximum likelihood. And then we can test whether m and sigma are the same for all firms, which would imply ergodicity, and leave d as the only parameter that would capture idiosyncratic factors affecting corporate profitability. The reason why d is the only remaining parameter then that would be able to account for idiosyncrasies is simply because it does not show up in the equilibrium distribution, which depends only on m and sigma, but not on d. Now, if you do this exercise, what you observe is that at 5% level, you cannot reject the ergodic hypothesis for 90% of survivors. So obviously it's not perfect, because at the 5% level, you would like to observe that you cannot reject for 95% of the firms. Yet it still seems to be a reasonable starting ground, or a good first approximation to assume that corporate profitability is ergodic. But the implication then is that there is no risk return of the risk return trade-off that would be meaningful in any way, because if the surviving firms are all experiencing the same average profitability and the same volatility, sigma, then there is no risk return trade-off that is meaningful to speak of in the first place. The speed at which firms will then experience fluctuations around m in this band of sigma, if you wish, will then be determined by d, or square root of d to be more precise. And viewed from this perspective, you could say that this diffusion model is then a very parsimonious dimensional reduction of corporate idiosyncrasies into one single parameter, namely d. Where does that leave us? Well, you see, in the jargon of complexity science, perhaps you would say something like M and sigma are emergent properties of the corporate capitalist system that is in place worldwide since roughly the 1860s. One question that we are really curious about, and where we are hoping for some feedback, would be to hear if you are aware of similar remarkable stabilities in other disciplines. Yeah, so perhaps in ecology, that would be our great hope. I mean, the first thing that came to our mind, for instance, was human body temperature, which is remarkably stable. And if you see deviations from it, it is usually a sign of serious illness. And the human body has to perform a lot of work and find its way in the environment that very often is hostile in order to maintain this body temperature. But talking to MDs so far, we were not able to come up with a metaphor that was somewhat similar to what we observe here. And subsequent to that, I guess a question would be, how can one part of an otherwise non-ergodic system be ergodic? Are we buying the stability in the rate of corporate profit at some cost? And we very much suspect so. So in this sense, is it perhaps necessary that we observe a lot of fluctuations in all the remaining economic and especially financial variables if we want to maintain such stability in the rate of corporate profit? So that's it from our end, and I understand that some parts of this talk must be rather cryptic given the time constraint, but it is our sincere hope that we will be able to engage in productive discussion during the live sessions at the conference. Thank you very much one more time for giving us the opportunity to present at the conference.